You're my favorite in this class. You're my favorite. All right. So we were talking about the CST, right? Or the constant strain triangle. Where everybody lost? You guys where you need?
I'll find it. Yeah, Dawes has some catch up.
Dawson has some catching up to do. Turned in your homework though, that's good. It's positive. That's due today, Aaron. Due today. You probably know where we're at too. You watched the lecture from Monday? Did you? Nah. I figured. Yeah, that's fine. I mean, yeah. Don't lie to me.
Tim, I was impressed when I came downstairs. I saw you soldering on Monday.
Why?
You're a man of many talents.
I am a man of many talents. I like to build shit. That's why I stopped working at Morrison Maryland.
You
And I
operate
do this
cranes
half
as
time.
well.
I operate cranes.
And when I was like, who's got the welder set up? They're like, Tim did it. I'm like, God damn.
Yeah. I was very fortunate in that when I was growing up, I started working in construction when I was 16. And I did that all the way through grad school. Like, that was my job. I didn't have an internship at an engineering firm. And so, yeah, it was fun. I was fun. So I could do other things, which I enjoy. I had a hard time being in an office all the time. It really wore on me after 10 years. So that's why I got certified as a welding inspector. So I could go out and inspect welding. So I could get outside, hang out with my homies.
You're going to like higher level construction stuff.
Because I also don't want to be forced to be on a project for like 2 years. Like
Moving around.
yeah, like that was another gripe I had about, I mean, not to, like, you guys are doing a great job, right? Heading where you're heading is awesome. All I gotta tell you is find what you enjoy, right? And that might change over time. I always thought like, oh fuck, I gotta start at a job and I gotta be there forever, right? You gotta put in your 35 years and I gotta retire. That's how I originally thought. And maybe it's just a generational thing. Maybe you guys are getting better at that too, okay? But that's what I felt, and so then I had this like big conflict when I got done going to school for 6.5 years here, right? And I get all these degrees and all this fancy shit, and then I'm like, fuck, well, now I gotta get a degree, now I gotta get my license, and I get my PE, and I'm like, well, if I really wanna be a structural engineer, I gotta get my SEs. So then I stay and I keep getting my SEs, and then I get all this certification, I'm like, man, I really still am not super stoked about this. Like, am I good at this? Yeah, I'm good at this. Could I continue to do it? Yeah. But do I want to? I don't know. So then I was like, fuck. So Mike was like,
Had a midlife crisis.
kind of, yeah. Quarter life crisis, all right? I'm gonna live longer than that. I'm gonna live longer than that, all right? And so then here I am, trying to figure it out, okay? Doing a little construction, still running cranes, teaching you guys about variational calculus, doing all sorts of random shit. Okay? Which is fun.
You
What?
you don't do your own CA?
At Morrison Maryland? Yeah, we did. But I ended up, because I didn't like working for architects, I ended up doing a lot of mining stuff. And so my projects were in Alaska and Nevada. So there was like a year there where I was gone a week out of the whole month, driving to bumfuck middle of goddamn Nevada, okay? Like you fly into Reno or Las Vegas and you drive, you get a rental car and you drive 4 hours. Literally like the center of the state. Beautiful, right? I'm an outdoors type of person, it's a beautiful place. If you haven't been in the middle of Nevada, I recommend doing it, okay? Just don't do it for a week out of every month for a whole year, okay? But that's when we would do construction admin. So then I'd be back in the office, you know, pushing RFIs and all sorts of shit like that, submittals. It was a big project, but, so I had a lot of rewarding things, but then it just in the end, I'm like, man, it'd be kind of cool to find some mixture of both, a better mixture, and so I'm trying to find it right now.
Were they salty when you left? Were they pissed?
A little bit, yeah. I had the best boss I've ever had in my whole life. She's amazing. She's actually in our Missoula office. And I could have done amazing things. Like I was on some of the bigger committees in the company where I was hanging out with all the gray-haired people, you know, and she afforded me those opportunities. But again, it's like, just look over, I'm like, man, this person's been here 42 years. And this is like their life. They identify with being the office manager or the market group leader of this corporate firm. I don't know. But having licenses, I'd say, like, go get licenses and keep them because it keeps doors open. A lot of doors. I could go back. I didn't have any bad blood when I left, if that's what you were getting at. they would take me back. And probably more so because right now, anybody will take an engineer.
How hard is it to get a teaching job without doing research?
So I am a non-tenure track faculty member,
It's just like an
and you're not
associate.
expected to do research. I'm literally just paid to teach.
Yeah, that's not like a super like common.
It is, I mean,
It is.
Doug
Yeah.
Smith,
Okay,
is
that's fair.
is what we would call an adjunct, I think now. Someone took offense to the word adjunct, and so now we're called instructors. So it's like, instructor would be like Audrey, myself,
Gotcha.
Doug Smith.
Isn't
What's
Anders?
that?
Matt Blank.
Matt was actually, yes, Matt Blank, I think is,
Kurt
yeah.
Manson.
Yes.
Just any, like one that's not doctor this is essentially one of them.
Yeah, see, so what you need is, in order to be in a tenure track faculty position, you need to have a, what they call a terminal degree in that department. So they offer a PhD in the College of Civil, or the Department of Civil Engineering. So in order to be a tenure track faculty, you have to have a PhD, which I don't have.
I think there obviously is pay increases with that, but it's.
Yeah, I mean-
See a lot more responsibility with it, with your research and more classes.
Yeah, but once you get tenure, then you're like,
Then you're Mike and you're.
yeah,
You're fucking around.
then the only, once you get tenure, you become an assistant professor, then the only benchmark after that is full professor. So that's really the only thing you have to, reach for. You get a pay increase at that bump, and then you have that job for life. But then it's like, do I wanna do this forever?
Yeah.
Like, I don't know. I've had fun. This is the third semester I've done it, and it's a good balance. And I'm half-time.
What's your other part-time?
I build, I'm a general contractor.
Yeah.
I do structural engineering consulting on the side. What else do I do? I think that's it.
Built anything yet?
I'm working on, actually just sent a bunch of plans for a single family home that I'm gonna build, hopefully this summer. And then I work at the crane service.
That actually is a good thing, 'cause in the summer you're not teaching.
In the summer I'm not teaching, but I usually fill it with other things. Pretty good at that.
You're doing the
Yes.
contracting and stuff.
Yep. Any other questions about Tim?
It's all about your day.
It's all about me day. It's all about me day.
If you get started on it, you might as well keep that.
Yeah. It's like, all I gotta say is you're not stuck, and your education is providing you a lot of opportunities to do other things. Okay? I would recommend all of you getting your SEs, alright?
How hard is that?
It's fucking hard. The gravity is not that hard.
That's what I've heard.
For the
Gravity's
gravity's
not
done
that.
in PE basically.
Yes,
Like it is your PE.
but the lateral one was tough. It was really tough.
Did you do it the first time?
I did them both the first time, but I didn't do them together. I did one, and then 6 months later I did the other one. Yes, and I passed.
I heard doing them together is.
Oh, it's crazy. Dan Van Lucian did them both together. Crushed them.
One after the other?
Yeah,
like
you
back
take them
to
on
back.
Friday,
Yeah.
because the gravity is offered when the PE is offered. So like you sit when everyone else take the PE, you'll take the gravity section of the SE, and then the next day they offer the lateral. So it's just like 2 8-hour days packed where you're doing both. I mean, maybe I could have, I don't know. I didn't try it, because I just didn't wanna have to deal with studying for both of those load sources.
Do you have like a portfolio of projects you have put together for that?
What do you mean? Like,
I don't know, I've heard like in California and Washington, a couple other places, you have to have like a professional portfolio put together for committees to like review.
yeah, so if you get licensed in those states, you have to show, you have to do a bit more than what Montana requires in order to get the license. One thing that I've always been told, you should get licensed in California because they have no continuing education requirements. So once you're licensed, you're done. Whereas Montana, it requires, I think it's 12 hours a year or something like that I have to come up with. But teaching is like huge for me, so I don't have to worry about it.
Isn't even California's the also, it's like the strictest, so like if you get certified there.
Reciprocity, yeah, if you were gonna try and get licensed in another state, yeah,
It's-
California
that's
would
the
be in
highest
pretty good.
standard, So therefore it should transfer to
Yep.
all other states.
But so I'm licensed as a professional engineer in Montana, but then a structural engineer in Nevada, because that state requires a structural engineer. So hopefully, if I had to go somewhere else with that, I could, use those as reciprocity to go somewhere else.
How much later after your PE can you get your SE?
You can actually, and like John Lubgren and Sam Fox did this at DCI, the state of Montana allows you to take the SE and use that to get qualified for your PE in the state of Montana. The problem with that is, if you were to then go to Washington State and try and get licensed as a PE there, they don't qualify the SE exams as the PE exam. So Sam went back and took the PE after she had taken both SEs. I went the PE and then SE's route because I'm selfishly into financially, Morrison Merrily gives you a pay bump, and I'm sure all other firms would do this, right? So I could take one test, get my license in Montana, and get the pay bump associated with becoming a PE earlier. And that trickles down for your entire career, right? I mean, that's more 401k contributions, that's retirement, that's everything.
There you get it.
Stock stuff with Morrison Merrily is tied to your compensation, so that was my motivation, to do PE first.
Ego boost to put your own stamp on your
Yeah,
drawings.
Kind of makes it scarier.
What?
It's fucking scary, dude. Like, you own it. The first thing I stamped,
Liability.
which is cool, like, I mean, like, yeah, you get to put your name on something or whatever, but it's a flume that transfers water from Highlight Reservoir over to Cottonwood Creek. So from Highlight Creek around the corner to Cottonwood Creek. And it's like elevated on this super steep hill, and talk about squinting. Like, I mean, when I was doing the analysis, right, we talked about snow lows and now you kind of have to mirror it, like, man, it's still running. It's still running to this day.
Didn't get ripped off the hill.
It hasn't so far. It hasn't so far. And I also feel good about it is because no one's generally around it, right?
Yeah.
So if it did fall down, the chance of there being a loss of life is low. So then negligence is probably pretty low, right? So, but no, it is pretty cool. Like, I put my name on the community center in Big Sky, so that was pretty sweet. And then I put some stuff in Nevada, but it's 4 hours from anything. So I'm like,
Yeah.
Aaron, go check out my shit in Nevada, bro. You go down there and you can only look at it from the highway because it's a closed site and you need like MSHA certification, escort, and all this other shit. So it's like,
See, kids?
yeah, basically.
Take pictures of it while
Basically.
you're there, 'cause you ain't showing anyone otherwise.
My wife's like, "Are you sure you were going to Nevada and working?" You know,
Were you going
like
to Area
she
51 or
cannot
what?
see, she can't see anything. I've done stuff in Area 51, like she can't. Like, sweet, I did it. I swear I did it. I mean, I don't even know if I'm supposed to tell you this.
I was gonna say,
So anyway, all right, we're gonna really work here today. Let's do something. All right. Any other questions?
was there
Good.
anything?
MTS, what do you have to say today? You are just always so quiet back there, and I always forget to call you out, and I told myself I was going to. Yeah? Did you go skiing yesterday? Do you ski?
Not much, but I tried twice.
Okay, well, that's good. This year you tried, or previous?
So this year once and previous year once.
Okay, so you're a once a year kind of guy. I'm a like twice a year kind of person.
Use the sled deck.
I do, yeah, ride my dirt bike more. I used to ski a lot when I was in high school. It was really cheap, got me away from my parents here. It was a lot of fun, especially when you start driving. Okay. So, I'm trying to remember where we were at. So we went through the constant strain triangle, right? We talked about this idea of whether we would consider, right? It with respect to our constitutive relationship, we kind of have two options. We have plane stress and plane strain. Talked about how one is more geared towards thin plates versus thick plates. We know that in structural engineering, we generally are landing in this plane stress case. I tried finding, because I've always just assumed plane stress. That might be wrong. That might be wrong in some cases, honestly. But I could not find a single spot that was like, oh, when your width to thickness ratio is this, right? All they're trying to tell you is that overall, right, you have this variation in stress across through the thickness, right? And so if we have a pretty thin element, it has to be zero on the surfaces, right? We're not applying loads there. If it's a different problem if we start not looking at it with respect to a membrane where we just have in-plane stresses. And so there really isn't like a real rule of thumb. It's kind of engineering judgment. And so thinking back to everything that I've done, I feel like plane stress is a valid assumption. Plane strain, you'd think you'd have to be putting stresses through a distance that is small relative to the thickness, right? Because then you would have a larger distance over which the stress could vary in the through thickness direction, right? Because that's what you're saying. It's not straining. That means it's really, really thick relative to the in-plane direction, the membrane direction. And so the point to where the thickness ends up giving you restraint, right? Where our strain goes to zero. And so you would then do the plane strain case, okay? So we're gonna do plane stress. We talked about how, again, we just do our potential. We use the principle of stationary total potential energy. We need to calculate our strain energy, U, our work done, W. We have this area under the stress strain curve, just as we have before. We end up with this equation that relates, right, our nodal degrees of freedom with our stiffness, and that gives us our strain energy. And then our work is just force over distance. In this case, we want to relate our forces to our distances with respect to our nodal degrees of freedom, right? And we would do that via our shape functions, right? So we replace our displacements in the U and V direction with our shape functions. And so we end up with this total work equation like you see there, which we talked about. Pretty sure we talked about it. Right, that's kind of where we stopped. So we have this principle of stationary and total potential energy, pi equals strain energy minus the work. So we're finding the stationary value, which essentially is saying we're going to take the derivative of the first variation and set it equal to 0, right? Delta pi or partial pi, like we did in our homework 4. And so if we do that, we essentially pull out one of our degrees of freedom. We essentially take the derivative with respect to a small amount of disturbance with respect to our degrees of freedom, our dt, so that dt goes away. We reorganize this and we get this total equilibrium equation or force deformation relationship, where we have all of our forces on the left-hand side, and those equal our stiffness matrix times our nodal degrees of freedom. One beautiful thing about the constant strain triangle, right, U and V, well, now when we look at looking into the global coordinates, right, those were local coordinates. So when we jump to the global coordinate sense, they're oriented in the same direction, right? So we don't have to do that transformation. So local, degrees of freedom aligned with global, therefore no transformation which is nice, right? Transformations just add more orders of operation in the whole analysis process. And so when we do bar elements and beam elements and things like that, right, there's a lot more going on because we have to do more matrix multiplications to transform things, and we got to go back if we're looking at local stuff. Well, in this case, our displacements are in the same direction, which is helpful. We also have, right, our local, right, we're looking at element by element, but we need to look at a global sense, right? Then we're going to have, say, 1,500 of these elements together, so our stiffness matrix is going to be a function of all of the elements combined. So assembly process remains the same.
It's kind of weird though, like, right, where you can't, it doesn't overlay like previously, like all on a diagonal, like you have a bunch of scattered assembly points because certain.
But it's still symmetric. Your K matrix
Yeah.
will still be symmetric. But yeah, I mean, you're
like
gonna
displacements that like you can't.
You're gonna
They don't just overlay like all nice like beams because like you might have different nodes sharing different
yes.
displacements. So
Yes,
all
so it's like
scattered
you,
the
yeah,
way
one node
assembly
2
is
on
all
one
weird,
is gonna
yeah.
be, say, node 3 on another.
Yeah.
Yes. The other thing is, right, B and E, B are strain displacement matrix. Because it's a linear strain triangle and we take the derivative of that, we just got constants in our strain displacement matrix, right, B. So B is a constant, E is a constant, right? It's just a function of the modulus of elasticity and our Poisson's ratio, and it depends on whether we're choosing plane stress or plane strain. So again, that both of those, because they're constants, those can get pulled out of that integral, right? Because they're not changing with respect to the volume. So since B and E are constants. The volume. They can be removed from the integral. So that means K just becomes, right? AT, A being the surface area, right? T being the thickness, that way we get the volume. BT, EB. Something like that. Which is nice, right? So if we step back and look at this overall, we have a 3-node elasticity element. How many degrees of freedom do we have? 6. We have X and Y displacement at each node, right? It's in plane, either plane stress or plane strain problems. We talked about having 2 different types of applied forces. What were they? Body forces. And surface tractions. Body forces deal over the volume. Tractions deal over the area, right? Because we have this 6 degrees of freedom, right? And we have 2 displacements, right? U and V, right? We had 6 generalized degrees of freedom. We split those in half, so we get 3 for the U displacement, 3 for the V displacement. So we ended up with this linear displacement field that we assumed, right? U sub x a naught plus a1x plus a2y, right? That's what we ended up with. We have this spatial field that's in 2 directions, x and y. We get 3 generalized degrees of freedom for each of our displacement field functions. So we end up with a linear function. So that means we get constant strain. Obviously, that's where the element gets its name. If we wanted to make this, and some of you in Ladine's class probably went over it, instead of a constant strain triangle, we wanted a linear strain triangle. What would we do to this plate to get a linear strain triangle?
You need to add a degree of freedom, right?
We'd have to add more than just a degree of freedom, right?
3, right?
We'd have to add 3. Well, we'd have to actually add 6. We'd have 6 nodes, and each of them have 2 degrees of freedom. So then a linear strain triangle, you'd have a node here, here, and here. Because in each of our coordinate, we need to add a polynomial, right? A quadratic with respect, because when we take the derivative of it, we now want a linear strain. So we need to have a higher order displacement function. So we end up adding in 3 more nodes. We'll talk about that a little bit later. So using the principle of stationary total potential energy, we ended up with this, right? So this is our, if we looked here, we call these our equivalent nodal forces, right? Energy equivalent nodal forces, which you guys are calculating for the homework. Yes, Aaron?
How do we impose boundary conditions such that you could like capture pin behavior when you have energy equivalent nodal forces that come in force, moment, force, moment?
Start again.
Like, we're not assuming support conditions in the homework, but how would we plug in force support conditions to,
Support conditions are boundary conditions which would impose displacements, right?
so basically, moments just drop out of the, like, right,
Or
we have,
implied moments.
Yeah, so what you are calculating is, what are you, like, you're calculating an R1, M1, R2, N2.
yeah,
So it's the nodal forces that are resultant of the loads that are applied between nodes. Because our finite element does not know what's going on between it and the node down the line. We
Yeah.
are assuming a displacement function, right? We just assume something's going to, we're assuming that it's gonna behave a certain way between nodes.
yeah,
And so the element wants to know, well, what's going on between the nodes, right? But that can only be related to nodal forces, right? Because the element only knows what's going on with respect to nodal forces. Because that's what this equation is all based off of, right? Nodal degrees of freedom, which means we need nodal forces. And so we take what's going on in the field and we relate it back to what's going on at the nodes, right? So we have nodal forces, we can have an R and an M, like forces acting at the nodes, right? Which you may have done in the first homework we did, right? Where we had the column, the concrete column. Some of you decided to distribute that load out over the edge of a area, which then spread it to the plates, right? Some of you decided to actually load it at nodes. Well, if you loaded it at nodes, VA is taking those and putting in this F vector, right? Those are actual nodal forces. If you decided to put a uniform load at the top of your plates, right? That uniform load, you need to then relate those back to what is that equivalent to if we were to load the nodes, because that's what the element actually cares about, is what's going on to nodes. So that's what these are doing, right? Where that uniform load is a traction, right? That's just happening on one edge between two nodes of that plate. And so then we say, okay, we're gonna split that traction up. We're gonna load node 1 with this amount of a reaction, node 2 with this amount of reaction. We're going to then, this uniform load is gonna wanna rotate that node also, right? Which influences what's going on at the node, which ultimately influences what's going on at the displacements.
so we can't necessarily relate back the forces we get in the homework to a pinned.
Unless you said.
Unless I give you boundary conditions.
And then solve for all that, and then solve for the forces that F equivalent would cause.
No, from a validation standpoint, no. I think,
Because you're not gonna have the same,
You
the
have-
moment's gonna cause a rotation, but then it'll cause a different, like, vertical force in the node for a fixed fix.
the only thing I didn't do, yeah, I was gonna say
Because I
fixed.
calculated the fixed condition and it's exact.
Okay, cause that, to me,
It's exactly the
that
same.
makes sense.
But it's not the
Transfers
same for
all
the
that
pin
force, not
condition.
displacement.
No, it wouldn't be a pinning
Yeah.
condition. Yes. For both the point load and the uniform load, right?
Mhm.
Yes. Any other questions here? Okay.
More questions than Monday.
More questions, more lively on Wednesdays.
'Cause Aaron's
Today's like
here.
the half day, yeah, Aaron's here, the disruptor. Today's the half day of the semester, I think.
It is?
I think today is the half point.
We're already halfway?
Already halfway, Brandon. That much fun, dude.
And we still haven't touched VA.
And we haven't touched, yeah, you have, you touched VA like the first week.
Said we touched
did.
it.
Oh, you only touched it once, yeah. We're gonna touch it a lot more starting tomorrow. Adam's gonna just enlighten you about. Because James said that I couldn't test you on anything that we haven't done in class. I'm gonna give you a couple examples here. What it's like to calculate a stiffness matrix, right, for a CSD element, given some parameters and some locations, nodes, and things like that. And we're also gonna go through some loading of an element. Yes,
What's the
Amanda?
last line of the previous set of notes?
The last line of the previous set of notes. That?
Says equals something.
Oh, shit. Oh, well, it's just based on the fact that those are constants, right? You need to get rid of the integral. So you end up with what we put up before, which was AT BT E times B. Is that right? Yep, that's right. Because our strain displacement is constant, it doesn't vary with over the volume. E doesn't vary over the volume, it's constant. And so then we just get the surface area times the thickness, right? Thank you, Amanda. There was one other thing that was supposed to be in this, and I think it's in your skeleton notes, isn't it?
No.
This guy.
Yeah.
It's not there?
Yeah.
This is direct from Adam Stordahl. I said he taught this class, right? So Dan taught it, that's when I took it, and Adam taught it. And in those classes, they talked all about theory, right? No VA. So now I'm saying, yeah, screw this, we're gonna run through this pretty quickly. I skipped a lot of stuff, right? We're trying to get to the point where, okay, do you guys have enough of the background information, right? Some of the major elements that are used in finite element software for structural engineers. Well, we talked about a bar element, a beam element, right? A second order beam element, quadratic bar, that's essentially just saying now we've got our axial loads and the quadratic bar, sorry, we add an extra node. It's like the linear strain triangle where we just, this is one element from U1 to U3, but we have 3 nodes in it, okay? So what does that do? Well, that allows us to have 3 degrees of freedom, so 3 generalized degrees of freedom. 3 generalized degrees of freedom gives us an extra order on our polynomial with respect to our displacement function. Right? So that allows us to have different strain relationships, right? Because you're going to take the derivative of that. So now we can have constant strain, or linear strain instead of constant strain with the normal bar element. So this just kind of breaks down. I thought this was helpful to have. Is it not? I swear it's in there.
No.
It's the last page of something. No?
I like it, but it's money.
Yeah, so it breaks down all of our elements, right, with respect to degrees of freedom, okay? Obviously, when we can add these two together, right? We just add degrees of freedom, so now we have the u sub x and the v sub x. So we have degrees of freedom, we have our displacement interpolation based on those degrees of freedom, right? Came from our generalized degrees of freedom, we get our number of A's. Strain, we know strain is just a change in length over the original length, right? Or with beam bending, it's the second derivative of displacement, right, times y, and so on and so forth for all of our elements. Stress, same thing. We are following Hooke's law, so we have this linear stress-strain relationship, right? What happens when we go to the second order beam? Well, that was when we start looking at buckling and large displacements, right? We start looking at what's the displaced shape start doing to our equilibrium. Well, now we have this coupling of the force over the area, which then contributes to the stress in our cross section. We have internal energy, which all of them are the exact same, except for the one that's coupled with respect to the axial load, which is our second order member, right? We had this geometric stiffness matrix that was developed in order to take into account the fact that the axial load is affecting what's going on with the stiffness. And then we've got the work of applied forces. Well, it's just whether or not we're always going to have our nodal forces, right? What's going on with the nodes. For a bar element, we can just have forces in one direction, right? For a a constant strain triangle, we can have forces in 2 directions, right? F in the x, F in the y. As we add on, we can have forces due to linear loads along the length, like our bar element, transverse loads. We can have surface tractions or body loads, right? And all of those, the work of those applied forces is just a force times the distance, right? And we relate that back to, instead of our u's and v's, we're related back to nodal degrees of freedom, and that's where our shape function comes in, and that's why we end up with this n sub t times v, right? Or n sub t times q sub x, which is our linear line load.
How is v of x equal to q? How do you make that substitution? V of x is equal to q of x.
Oh, no, what he's saying here is, for the bar element, work of applied forces equals this. For the beam element, consider this as in its own cell, that work equals this. separate things.
And is that Dave-X, is that when we had like the Q of X and the W of X, or when was that? When did we have the two there?
When we combined a bar element and beam element,
Okay.
which would just be the two of them added together,
Yeah.
right? When we set it stationary, right, we're trying to find equilibrium, we set the first variation equal to 0 in our case, because a lot of times if we drop out of the integral, we can just, or it's a definite integral, we can just take the derivative, which we did a lot of times in the homeworks and things, right? So we take the change in potential energy. Ends up happening is one of these displacements drop out, right? We're taking the derivative, this is really, right, we start with strain energy, which is 1/2 dt, blah, 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 times d, well, this is really d squared, right? Well, if you take the derivative of this, d squared, 2/2, the half drops out, we just end up with 1d, that's what ends up happening here, we end up with 1d. So stiffness equals our forces, right? Force displacement. It's kind of our spring case, right? Just linear spring is really what it ends up being. Everything ends up being. Okay. So this is nice. I'll make sure that that's out there. It should have been out there. I thought I had it on the skeleton notes. I do in here for some reason, but maybe I obviously messed that up somewhere along the lines.
Yeah, make it a separate.
I'll just make a separate note for it now. So, let's go through a couple examples. They're really straightforward and easy. I'm just gonna show you, right? This is a example of a single element. Right? It has nodes 1, 2, 3. Those nodes have coordinates spatially, right? In X and Y. Those coordinates spatially line up with global coordinates, so we don't have to do any transformations between our local sense and our global sense. This plate, for instance, I'm gonna say that it's steel, so it's 29,000 KSI for modulus of elasticity. Poisson's ratio for steel is 0.3, and I'm gonna say this plate's 1/2 inch thick, right? So overall, our dimensions are 2 by 3, right? This is a half of a square, or a rectangle that's 2 by 3, right? I'm gonna assume plane stress because of those dimensions, right? I'm gonna assume that that 1/2 inch is thin enough that over the length of 2 inches and 3 inches, that it's going to act, right, in a plane stress case where the stress in the z direction is close enough to 0, we can assume that, right? All these coordinates I'm gonna say are in inches. And so going back, because it's a constant strain triangle, right, our strain displacement matrix is constant. Our E is constant, our thickness obviously, and area becomes constant. And so we can just calculate those out. Well, we need the B matrix. Well, if you remember from the notes, it was this glob of stuff, right? This 3 by 6 matrice. Our plane stress matrice E was this big glob of stuff. Area, well, that's as easy as just finding the coordinates and figuring out the area, right? 1/2, base times the height, base is 2, height is 3, 3 square inches. Thickness is 1/2 inch. Well, now that's pretty simple, right? We just plug it into MATLAB, figure out our strain displacement matrix. Remember the nomenclature here for, right, y23, well, that is the y at the second node minus the y at the third node, right? Y at the third node minus the first node, y at the first node minus the second node, so on and so forth. So we can just develop our strain displacement. We need our constitutive relationship. Well, that's based on plane stress or plane strain. We're going to use plane stress, develop that equation. Stiffness, boom, just like that, right? And as you see here, Elias, right, it's symmetric about that diagonal. So now I can test you on that. Okay, easy enough. What's another thing we deal with, right? We deal with loads, right? And as we talked about in class, right? A surface traction, right, would be something that, like a uniform load or a load over the area. Well, in structural engineering, a lot of times those come from, say, wind loads, seismic loads, collector forces, right? Forces that are along just either, they could be in the x direction from 1 to 2, In this case, I'm gonna do in the x direction between 2 and 3, right? So it's a uniform load that's acting between nodes 2 and 3 at 0.1 kips per inch. Right? So that could be the leeward wind pressure, right, resultant that comes from the wind's blowing this way, right? Leeward's on the far side. We have a suction pressure that's on this wall. That suction pressure is going to span, this wall is going to span from the floor to the ceiling. So we're going to take half of that load, we're going to put it up to the ceiling, we're going to say that that acts as a line load, and we're modeling our diaphragm as a series of all of these CST elements, right? And I'm looking at one element, and we're going to take that load is 0.1 kips per inch along the length of that, the edge of our diaphragm. We're going to look at what's going on, right? Obviously, there'd be a series of other elements that are meshed through here, and those meshes would then have some of those nodes would have to have some boundary conditions, right? It's got to be stable. So we wouldn't want the whole diaphragm, if I put a load on it, just to move as one rigid body. It's going to have restraint. So at some point, we put, as structural engineers, restraint at the edges of that boundary, right? So it's coming in at the edge of the diaphragm. This diaphragm acts as one huge deep beam that spans between, say, the back and front wall of the classroom. If we were going to be modeling the shear walls, which were the back and front wall of this classroom, right? And we passed the diaphragm, we wanted to do all that by hand. We said, okay, it's halfway up. Okay, this acts as a deep beam. It's just one diaphragm. Say the box of this classroom was our building, right? We're going to say that it's simply supported between our two walls. So we're going to just put a line load on a simply supported beam, right? WL/2, that would be our reaction. We'd take that reaction, we'd divide it by the length of this wall, and we would have a line load that we'd be applying to this wall. If we wanted to analyze this wall in VA, we would model it as a series of CST elements, right? That we're running now vertically, and we would have a line load that's acting, right? In this case, it might be a line load that's acting all in the x direction between nodes 1 and 2. Does that make sense? That's how those could relate to what we're actually doing, right? Or a midterm exam. Okay.
0.
What's that? Am I out of time? Fuck!
Are you surprised?
No more talking about Tim, okay? We're done. You guys heard all about me, we're done. Shit. All right.
You're getting ready there for another round.
Ah,